Yeah, welcome everybody. In this talk, Till and I going to talk about two different kinds of stream processing applications, streaming analytics and complex event processing. Till and myself were both committers at Apache Flink and currently working at Data Artisans. So you might have noticed stream processing is really picking up. It's one of the dominating topics here at this conference and also at previous conferences. And this is because most data is actually produced as streams. So there's usually not a one big block of data that you try to analyze, but data is constantly produced. So may it be coming from server logs or application logs, click logs, mobile devices. Internet of Things is another big topic here. So data is constantly produced and arrives in data centers. And so now people are thinking about, okay, how can I really leverage this continuously produced data? What can I do with it? And how can I analyze this data as it arrives? And there are different kinds of applications and use cases for this. So one of these use cases is complex event processing. So the goal of CEP is to usually detect patterns in an event stream. And then whenever you detect a certain pattern, you want to assemble or merge or aggregate a new kind of event that aggregates the events that basically triggered this pattern or triggered this pattern. And there are numerous applications for this kinds of workloads. For instance, there is process monitoring. So imagine you have a warehouse, have tagged all your items with RFID tags, and then you can basically automatically or get automatic events whenever something enters your warehouse, whenever something is moved within the warehouse, or whenever something leaves the warehouse. There is intrusion detection for networks. So whenever a certain suspicious pattern occurs, that some port ranges are tested. So these are kinds of patterns that you can try to detect from server logs, and or for financial trading. So whenever you see that certain buy or sell patterns occur, you can trigger certain actions either to buy stocks or to sell stocks. And these kinds of workloads are very demanding if you want to execute that on a stream processor. It's very demanding on the stream process because you need very low latency to actually do that. So you don't want to react like 1 minute after a certain pattern occurred. You usually want to detect the pattern instantly and also instantly trigger an action. So imagine a certain pattern occurs in a stock. You want to instantly react. You don't want to wait for 1 minute and everybody else has already leveraged this certain event, and you're basically the last. Another thing that's very important is you need to be able to take the time when the event was created into account. So it's not enough to whenever you detect patterns, it's not enough to detect the patterns on basically looking at the time when the event arrives at the operator or at the processing at the data processor. You wanna take the time when the event was created into account. So this is what we call event time, and you also don't want to lose certain patterns, right? When you lose an event or an event occurs twice, this might mess up your pattern. You might not be able to detect that. Another application for stream processing is analytics. So this is like the traditional approach to analytics, like the batch approach. So you have clients updating transactional database systems, and periodically you load the data from the transactional database into a data warehouse or HDFS, and then periodically you analyze the data in this batch store using a batch engine. And the problem with this is there's a delay, right? So whenever you do this periodic ETL, there is some delay. If you do that once a day, your data might be 1 day old when you analyze it. So stream processing or stream analytics is an application where you basically try to analyze the data as it arrives. So you get continuous results, and the data is basically analyzed as it arrives. You can also think of this stream analytics as a superset of the previous batch analytics, right? So if you consider like a batch being a finite stream, so whenever you read something from a file system, this is basically a stream. So even like the programming languages consider this as a streaming abstraction. So this is just a finite stream. So batch analytics is kind of like a subset from stream analytics. And the requirements on the stream processor, if you want to do such a workload, is need to be able to cope with very high throughput. So there are use cases where millions of events arrive per second. So your stream processor needs to be able to handle that. So massive parallelism is required here. You also want to do that, of course, exactly once. You don't want to count some things twice or lose data. And again, event time is important, and also like advanced windowing capabilities. What I'm going to talk about these briefly later. So as I said before, Till and I, we're both committers at Apache Flink, and this talk will also be about how Flink handles these kinds of different applications. And Flink is a scalable data processor that for streaming data. And it actually meets the requirements of both of CEP and streaming analytics. So it provides low latency, which is required by complex event processing, and also high throughput, so you can scale out Flink and achieve very high throughput with the system. Flink also supports event time, has very good support for windowing, and features exactly one semantics. And so the core programming abstraction or API for Flink is the so-called data stream API, which is available in Scala and Java. And this is, I would not say it's not really a low-level API, but it's if you want to implement like something like a certain detecting patterns or certain kinds of stream analytics, there is some overhead involved if you want to implement that. So this talk will be about introducing or showing some new APIs that Flink has recently added or will add with the next version. And these APIs are for complex event processing. So with version 1.0, so which was released, I don't know, maybe 2 months ago, we added this Cep library, which is basically a library to define patterns and actions, so what to do when a certain pattern occurred. And the community is currently working on stream SQL, so basically a way to ease the definition of stream analytics queries. We'll also briefly talk about how these two different kinds of applications can actually be merged, or show you some applications where it makes sense to combine CEP and stream analytics in the same application, and why it's a good idea to use a stream processor that's actually capable of doing both, like providing low latency for complex event processing and high throughput for the analytical part. All of this, I should say, is still quite early work, as I said. So CEP has been added with a latest version of Flink. Stream SQL will be released for the next version, and so this is all basically very, very early. So now I'm going to talk a little bit about a use case that we use like this, the driving example in this talk, and this is about tracking events in an order process. So this is a very, very simple example here. We have on the left-hand side we have the customer. The customer places an order at a warehouse. So first event, and the warehouse generates an order received event whenever it receives such an order. And then somebody in the warehouse will go assemble all the parts that the order requested in a package. Whenever the package is ready, the package is given to a delivery service. So whenever this happens, there is order shipped event triggered and sent into the data infrastructure of the company. And whenever then this order is actually delivered to the customer, then the delivery service will again send an event, say, okay, this order was delivered. So it's a pretty simple thing. So we have the order received at the warehouse, the order is shipped, basically leaves the warehouse, and then the order arrives at the customer, the order is delivered. So these kinds of events are in our use case. The order received, we mark that with this small envelope icon. The order shipped is the package, and then the T-shirt is when the package arrives at the customer. He unpacks the package and receives his nice T-shirt. We're going to model that as a stream of events. So the events are very simple. They're just three attributes. So the first one is an order ID. So we want to be able to track the different orders. There's a timestamp whenever this event occurred. And the last one is a status, which is received, shipped, or delivered, depending on what kind of event happened. Yeah, so this is the use case that we're going to talk about in this talk. Now I'm talking about the stream analytics side of this talk, basically aggregating this data. So I talked before a little bit about the traditional approach, where the data was loaded from the transactional databases into an data warehouse or HDFS or whatever other data store. And usually what you do when you have such an infrastructure, you usually issue repeated queries over changing data sets, right? You say, okay, give me a report for the last week, give me a report for the last week, and so on. So it's usually the same query with different parameters, but all over again. So you repeat the query. And these queries tend to join and aggregate large tables. So this is the traditional batch approach. When you now look at how stream processors do that, so stream processors, if you do that with a stream processor, you don't issue multiple queries. You just start one query, and this is like a standing query, so the query does never terminate. It consumes a stream of events, and it produces a stream of results. So there's one query which is active the whole time, so the data is ingested into this stream processor. The processor does some computation, aggregation on the data, and produces the results. And as I said before, so usually there are lots of use cases where this is actually done on very high volume streams, so where millions of events enter the system per second. But now one question arises: so how can you actually do aggregations on stream? So the stream is infinite, so it does never end. When can you close your account aggregation, for instance? So this problem is solved with the concept of windows. So windows split an infinite stream into finite batches. So one of these batches is called a window. And in this window, you can then, it's a finite thing, you can compute an aggregate. So it's very simple. And there are different kinds of windows. So the most common ones are like a tumbling window, which has a fixed size, and tumbling windows do not overlap. So you say, for instance, I want to count how many orders arrived in each hour. So then you start at 11 o'clock. The window is then collects the data from 11 o'clock to 12 o'clock or to 11:59. And then once you're at 11:59, you then say, okay, this window is closed, I can do my aggregation and emit the result. So this is the tumbling window case. There are also sliding windows, which have a fixed size, but you also say, I want to count, let's say, every 5 minutes, data worth of 10 minutes. then you basically start a window every 5 minutes, and every window has the size of 10 minutes. And to make this, in order to obtain consistent and meaningful results out of this, you actually need this support for event time. Because if you have an operator which says, okay, collect me data worth of 1 hour, and this 1 hour is basically determined by the operator or by the machine looking at the wall clock time, then this basically then the result determines, or the processing speed of this machine determines the result, right? So if this machine is very slow and can only consume very, very little data in 1 hour, the result will be different from a machine which is very fast and can consume a lot of data, right? So you want to have the result being independent of the processing speed of the system, of the machine, and so on. And this is why this support for event time is very crucial. When you use event time, you look at the data in the records, in the events, and this one basically determines whenever you can, what goes into which window, and when a window can be closed. So here's exactly this example here, counting orders by hour. So we have this event stream here, and the events arriving at the system. We have at 2 o'clock, from 2 o'clock to 3 o'clock, there's just one order arriving. So here the purple envelope. So when the logical time of the stream processor arrives at 3 o'clock, it says, okay, let me count what I got in this last hour. And then it says, okay, I just got one order, so the result is 1. And so on for the others. How can that be expressed in Stream SQL? So basically the work that we're currently doing in the Flink community. So here's a simple SQL statement that exactly performs this computation. So we have a select stream, which is a little bit different from regular SQL. So we have this stream keywords here, which basically says, okay, the result is going to be a stream, and the table from which I read is also a stream. It says from events. Events is the stream, the input stream. Like in regular SQL, this would be like the table. Then we have the where clause, where we put a predicate, a local predicate. We say, okay, we're only interested in the events with the status receive, so we only want to count how many orders arrived at the warehouse. And then in the group by clause, there's something special, right? So there's this tumble function, which basically computes a window ID. So the ID in which window a certain record will be aggregated. And here you say tumble timestamp. So we're looking at the timestamp column of the events. So we want to make this. Want to use the time of the event to compute the aggregates. And then we say interval 1 hour, which basically means, okay, so every hour, so I basically round down the timestamp for each hour, and with each for every record that arrives with a certain timestamp, I can put this record in exactly one bin, one group over which I can aggregate. In the select clause, you see the count star as count, so this is like a regular aggregation function which is evaluated on the window, and then it says also tumble start, which is just a function to determine the beginning timestamp of the window. Yeah, this slide is a little bit about the implementation details behind how Flink is going to implement this Stream SQL feature. So we are heavily leveraging Apache Calcite. Calcite is a SQL parser and planner framework. So it comes with has its own SQL optimizer, and is very, very extendable. So we are using that. So it also has its own catalog. So you can register data streams or data sets. So the same feature can also be used for SQL over static data sets. And when a SQL query comes, the Calcite parser takes the query. So the syntax I showed before is basically taken from the Calcite project. It parses the SQL query. It looks up the tables in the Calcite catalog. It then generates a logical plan. So whoever is familiar with query optimization, this is basically like a blueprint for a query optimizer. We then pass the logical plan to the cat-side optimizer, and depending on whether the query will be executed on a stream or on a data set, so whether it's going to be analyzed as static data or streaming data, we use different routes for the optimization, and then generate either a regular data set API plan or a data stream API plan. So all of this is basically compiled down to the regular Flink APIs, the data set API for batch processing or data stream API for stream processing. All right, so with this, I'm handing over to Till. He's going to talk about the CP side and how CP and stream SQL can be integrated.
Yeah, thanks, Fabian, for the great introduction to stream SQL. I'm Till, and now I'm going to talk a little bit about pattern detection on event streams using complex event processing. So consider again the use case Fabian just presented to you, the order fulfillment. But this time, we not only want to count the number of orders we've received within the last hour, but we want to monitor the processes a little bit more. So, for example, we would be interested in detecting when a delivery is delayed or even lost, so that we can inform the customer or send the customer notification to improve his user experience. Or other interesting information would be how long does it actually take from receiving an order to preparing the item to giving it to the delivery service. And that can be done using complex event processing. But first, we have to define for the different processes the service level agreements to distinguish when a process is delayed or when it is successfully completed. Furthermore, we introduce 4 new events which represent the results of the CP computation. So we have a process success event, which tells that the receiving an order and the preparation of the item, giving it to the delivery service, was successfully completed in time. Then we have the process warning event, which tells that it has not been completed in time, and the same holds true for, or the same things for the delivery process. So when you see, for example, a delivery warning event, you know that you can tell the customer that his shipment might not be delivered in time. Since all theory is gray, let's take a look at a concrete example. So we have again our stream of input events, where the letters are the orders, the parcels are the shipment events, and the T-shirts denote the successfully delivered items events. So what we are now looking for is events which don't have a corresponding successor. So for example, if you take a look at the blue parcel, it is not succeeded by a blue T-shirt, which would denote that this parcel has been given to the customer. So if we don't see such an event within a given time interval, so for our use case, I think we will see it later on the slides, it's 1 day, we want to generate this delivery warning. And the same applies to the order events. If we don't process the orders in time, then there are some problems in our warehouse which we have to fix. So these warning events can trigger some kind of countermeasures to solve these problems. But we are also interested in successfully completed events. So if you take a look at the green letter, we see that it is succeeded by a green parcel, which denotes that the internal processing has been completed. Now we're interested in the time it took. The same applies to the green parcel, which is succeeded by the green T-shirt. Okay, how would we model that with Flink? So first of all, we have to define what successful processing action means. That is, if we receive an order event, we also want to see here a blue parcel, which is a shipment event within 1 hour, for example. If we see that, we are safe and we can generate our processing success event. if we see the order event and it is not followed by this shipment event, we want to generate the process warning. So in order to define the success pattern, we have to do the following with Flink. So first of all, we define a pattern consisting of a starting event, which is identified by the name received, and additionally has a subtype constraint. So event is the supertype of all events. So the order, shipment, and delivery event. And so without the subtype event, every event would match to the first received event. But since we are interested in order events, we tell the system that the event has to be of subtype order. Next, we say that the order event has to be followed by an event called shipped. Here, this event must be a shipment event, otherwise it wouldn't be a valid pattern. So we could have specified again a subtype constraint. But to show you that you can also specify more complex conditions, I used the where clause, where I check the event or the status of the event that the status equals shipped, which is the case for all shipment events. And additionally, we define a time interval for a valid pattern. So we say that the pattern must occur within 1 hour, otherwise it times out. Okay, after we've defined this pattern, we apply it on our input stream of events, which is keyed by the order ID, because we want to do this pattern matching for every order individually. And the result is this processing pattern stream on which we can apply a select clause, which basically generates the result of these complex event processing. So here, as a user, one defines 2 functions. The first function is the timeout handler, which is called for every partial match, which has not been completed in the given time interval of 1 hour in this case. And since we wanted to generate the process warning in this case, we simply return a process warn event as the result of this timeout handler. The second function to this select call is the user select function, which is called for every successfully matched pattern sequence. And here we simply return the process success event with the order ID, the timestamp of the shipment event, and the duration it took from like receiving the order to sending the item to the delivery service, or giving the item to the delivery service. And we basically do the same for the delivery success and warning events as well, just with a different like time interval. Okay. So far, so good. We've seen how we can analyze event streams and generate results from it using complex event processing. But what if we are also interested in like calculating aggregations on these newly generated events? That could be interesting, for example, to calculate the number of delayed shipments per day so that you can assess the reliability of your delivery service, for example. Here in our example, we see that, that we have, in the first day, we've 2 delivery warnings, which means that 2 deliveries were delayed. And on the second day, we see that we have 3. So it's basically counting these the results of the CUP, the delivery warnings. Another interesting metric for a business could be the average processing time. So how long does it take from receiving the item to processing it and giving it to the delivery service on average? So this kind of aggregation is a natural fit for for stream SQL. So what we are doing now is combining both approaches. We first have, as a result, a data stream of either delivery warnings or delivery successes as a result of our previous CEP processing. And we now filter out the delivery success events because we only want to count the delivery warnings. Next, we have to register this data stream, giving it a unique name to reference it from a stream SQL statement. And last but not least, we can apply our stream SQL stream SQL query, the one you've already seen for counting like orders per hour, just this time delayed shipments per day, I think. Yes, on our data stream of delivery warnings. That's it, basically. That's quite nice, but it still feels a bit clumsy, right? It's, I mean, on the one hand, you have the stream SQL, which is really declarative and easy to use, and on the other hand, you still have to program Java. So it would be better to have like all declarative language for both things. So what we are currently working on and what's our vision is to unify the CEP and stream SQL so that we have a CEP-enriched stream SQL language. And with this language, the second use case, like calculating the average processing time, could be realized, well, in the way you see on the slide. It's not carved in stone, so it might change. But here we see that we have a nested query. The inner query calculates the pattern. There we see that we want to detect an event A, which is followed by B, and partitioned by order ID, so that we do it per order, and ordered by the timestamp, so that we have event time guarantees. We say that these two events have to appear within 1 hour, and that A, the status A, should be received, and B should be shipped, which is equivalent to A being an order event and B being a shipment event. And for these two events, we calculate the duration, which is then the input for the outer query, which averages them and per day. That's it basically. I think that's much nicer, and than like mixing like Java programming with SQL. Okay, that brings me to my conclusion, or to our conclusion. So what have you seen today? You've seen that Apache Flink is well suited for analytics as well as CEP workloads. It offers like intuitive, easy to use APIs for SQL as well as CEP, which gets you easily started and helps you to get your problem solved on a high level. And the combination of both things allows you or opens up even a new field of applications where you not only can do the usual SQL things, but also can easily detect and extract temporal patterns in your event streams, which well, allows you to extract more information out of your data. And that brings me only to two things which are left. One thing is to draw your attention to the upcoming Flink Forward conference, which is taking place at the same venue from the 12th to the 14th of September. So if you have experience with Flink and want to talk about it, then, well, please submit a talk and talk about it. If you're not that far yet, but still want to hear more and learn more about Flink, then get a ticket and, well, listen to others talking about their experience with Flink. It's a cool conference, I can tell you. And if you can't wait that long and want to get started and working on Flink and even get paid for it, then check out the careers webpage of Data Artisans, because we're currently looking for new hires for our team. Yeah. Thank you very much for your attention, and I hope you have enjoyed the talk.
Thank you, Till. Thank you, Fabian, for this talk. And we have some time for questions.
So if you do window operations, where do you keep state, and what do you do if the state becomes excessively large?
So the state backend in Flink is actually pluggable, so there are different kinds of ways to store the state. So right now we support, or Flink comes with 2 different state backends. One is basically the JVM heap, which is very fast, and of course, yeah, you can run out of memory there, so it doesn't grow infinite. Another state backend is using RocksDB, so which is persisting to disk. So and the state is regularly back-upped to a stable storage like HDFS, or and then when a failure occurs, it's basically yeah, restored from there.
More questions?
Hi. What's the roadmap for Stream SQL, and when can we expect aggregates?
Yeah, tricky question. So actually, what I've shown here is not working yet. So this is more like a look into the future. So with the next version, so Flink 1.1, we will have support for very basic Stream SQL support, which includes filters and projections and unions. So this is rather made for transformations, or transforming a data stream. And then we'll basically address the next features, windows, aggregates, and possibly even joins for the next version for Flink 1.2. So Flink 1.1, yeah, I mean, in the end, it's a community decision, but I would say 6 weeks are realistic for pushing out a 1.1 release.
Thanks.
I think we have time for one more question.
Hi. In the examples, you're using the timestamp of the event. So is there an easy way to deal with the delayed messages, the messages that arrive after the window?
Yeah, so that's a very good point. So I was a bit simplifying here. So when you look at the event, at the time of the event, you cannot really guarantee that the events arrive in order, right? So the events might arrive out of order. Flink is using the concept of watermarks, which is basically like an upper bound for the current time. So whenever a window operator receives a watermark which says, hey, it's 3 o'clock, no more events should appear that are before 3 o'clock, then we close the window. Of course, it might happen that there's still one more event or more events before that time, but Flink is also able to handle these kinds of events. You have to write custom code for it, but in principle, it's possible.
Thanks again. And if you want to learn more about Flink, then just come back to this room after lunch, where Till and Fabian will have a workshop. So perhaps we should rename this room from, instead of saying Frank Salon, this will be Flink Salon. See you after lunch.